The question is, what is the pressure at that spot, at the bottom of this tube?
Well, I guess if it's incompressible, it should be the same as pressure applied on the surface of the water.
No. So the pressure here is the same as the pressure here? Yell something out. Now, everything on that surface, everything on here, this would have the same pressure as that, same pressure as that, same pressure as that. I agree with that part. But I'm below the water.
You would add the pressure in the
Depth.
Pardon?
The depth.
Yes, we need to take the depth into account. So the pressure there is going to be whatever the pressure is out that atmospheric pressure, piece of O, plus what's the pressure at that distance y1 below the surface?
Rho gy.
So the density of the fluid times acceleration due to gravity times y1. So that is going to be the force being exerted on the liquid in the tube from the stuff that is not in the tube. Now the stuff in the tube, we got mg, which is just the density of the fluid times the volume of the fluid in the tube, g. And the volume of the fluid in the tube, well, I know the area, cross-sectional area is A1, and the depth of this is y plus y1. So this becomes rho times A1 y plus y1 times g. And those forces should be equal to each other. Or there's always a possibility that it's all been lies. So I have A1 times rho, or not rho, that's P. Let's try that again. A1 times the atmospheric pressure plus rho F G Y1 is equal to rho A1 Y plus Y1 times G. Now what?
Can you cancel the area?
Okay. Now what?
Can you expand and collect like terms?
All right, so I got EO plus rho F G Y1 is equal to, you said expand? I assume you meant distribute.
Yeah.
Rho Y G plus rho Y1G. They're all over fluid.
to subtract the rho g y1.
And what we're left with here is that the atmospheric pressure is gonna be equal to rho FG times Y. For whatever fluid you have in there, we assume that the density of the fluid is relatively constant. It's close enough to incompressible. G, we assume the acceleration of gravity is not significantly different at the top than it is at the bottom. And yeah, I'm just trying to picture how big that would have to be in order for little g to change. But it comes down to that the length of the column in the tube, the depth of the column, or the height of the column, y, is directly proportional to the pressure on the outside, thus a barometer. So when the low pressure system comes in, the column will fall. Now, if we use water as our liquid, let's figure out under a normal circumstance, how tall does that how tall does that column need to be if this liquid is water? Well, I know an atmospheric pressure somewhere around 100,000 Pascal. So 1 times 10 to the 5th newtons per square meter. And that's gonna be equal to the density of air, density of water, which is about 1,000 kilograms per cubic meter, times G, about 9.8 meters per second squared, times Y. What is the length Y? What would it need to be?
I'm getting 10.204
Units?
meters.
So if we wanted to create a water barometer, we would need to have that tube more than 10 meters tall. Because we need some wiggle room. We need to have some space at the top for the thing to expand in high pressure. So obviously, water not particularly convenient. But if we use a really dense liquid, for example, mercury, the density of mercury is 13,600 kilograms per cubic meter. And so we'd end up with, so this was with water, and then mercury. If you plug in 13,600 instead of the 1,000, what you get? Which is definitely much more manageable if you can get a hold of that out of mercury. Come to think of it, how do you get mercury? Is it just found? Or do they make it? Okay.
Well, how do you make an element?
Well, sometimes it's becomes as a product of a reaction. I mean, we can make helium by smashing 2 hydrogens together. But in essence, it's all about having the right number of protons in the nucleus and probably the right number of neutrons to make it sure it's stable. So you could take an element near it and slam a neutron or a proton into it and hope it sticks.
Like a bar of gold. Like a bar of gold, you just kind of.
Yeah, I mean, you can make gold, but the cost to make it is more than it's worth. All right, we'll take a break right here. When we come back, we'll get into continuity, which will relate more directly to the lab that you did last week. And then that will slide into Bernoulli and what is and is not a demonstration of Bernoulli effect, and why physicists don't care. At least my opinion why they don't care. All right, let's talk about continuity. So we have a certain amount of volume that is passing off to the right there. And the whole thing is a fluid, the same fluid, and we are assuming incompressible, of course. So in a certain amount of time, I'm going to have a certain amount of mass pass by this particular point right here, and in the same amount of time, I should have the same amount of mass passing a point here. In other words, as you narrow down, you have to speed up. Imagine that you're on the highway and you're about to lose a lane. If we assume that the distance between the cars does not change, then as the people go to the narrower section, they're going to have to speed up. Unfortunately, cars are a compressible fluid, so they slow down when you lose a lane. So the volume here is going to equal the volume here. So V1 equals V2. May as well just call it V. The volume that passes by a particular point here, the same volume passes by there, so that is just the volume that passes by it, so dV1 equals dV2. I know that the volume is just going to be the area of that particular cross section times that length. If this is delta x1, delta x2. Or if I call it x. Anyway, we end up with a dx1, a1 dx1 equals a2 dx2. If we are talking about the same increments of time, in other words, divide by some time differential, we get a1 v1 equals a2 v2. That's the continuity equation. So as you go into a narrower space, it needs to speed up. The book labels this, and I assume it's true, I don't deal with fluids, but in enough other context. Volume, flow rate. So for an incompressible fluid, the volume flow rate is constant. Let's relate that to the lab. Because in the lab, you've got basically a truncated cone here with a hole. I know that I have fluid flowing basically down and out of the hole. That the rate at which this falls is related to the rate at which it comes out based upon that. So if I call this 1 and call this 2, A1 V1 equals A2 V2. But the question is, what is the area? At some moment in time, what is the area? Or more specifically, that was assuming the area was constant. Area is not constant here, so this formula is more complicated than that. I know the change in volume at 1 is equal to the change in volume at 2. And the volume here is, well, there's my volume. And that is the truncated cone, which is 1/3 pi h r squared plus r plus little r squared. Dimensionally works. Yeah, I'm feeling decent enough about that. Little r is this radius right here. Big R is this radius right here. And h is this distance. If you already worked through this, I don't have to go over it if you've already done it. I'm not quite sure how to interpret the stairs.
Oh, I believe I have.
Okay.
I did something. It didn't look like this though.
There are other approaches. So we'll see where we end up. Okay, so what I'm really concerned with is the change in the velocity. I know that, at least at this hole right here, my area is not changing. Here my area is changing because it's getting smaller, but here my area is not changing. So this over here should be just area 2 times the velocity of 2. We just need to figure out this part right here, based upon that. So we've got, well actually, how many variables do we have here? Volume is 1. What else is changing?
Height.
Okay, and
Radius.
which one?
Big R.
Yeah. So we got 3 variables there. We need to consolidate. We need to get big R and h in terms of the same thing. So if I think about the cone, I have some initial height to it, and I've got some initial radius at the top, and then the bottom, that doesn't change. I know this distance here is r because I just created a rectangle there. So at some distance h here, I have some distance, big R is the radius. Again, it's a full cup, I'm just looking at half of it. So if I look at the big triangle, this is h naught, this is r naught minus r, because I'm looking at the triangle here, not the trapezoid, but this triangle right here. And that should be proportional to the smaller triangle. Will it show up? Well enough. So my smaller triangle, that's h. This distance right here is just whatever the radius r is minus little r, so this is big R minus little r. and there should be proportional. R sub naught, H sub naught, and little r we have measured beforehand. What we don't have is big R without the subscript and H, but with the triangle, with the similar triangles, we can do that. Now, the way I originally had it set up in the lab is I asked you to find the slope, find that slope right there, which would be the same angle as that. In essence, the slope is just HO over that. It's the tangent of that angle is the slope. But I have H is to big R minus little r is equal to H sub naught over R sub naught minus little r. So I want to keep H. And so I need to solve for R here. So I have little r, big R minus little r is equal to H over H sub naught, R sub naught minus R. So big R is equal to H times R sub naught minus R over H sub naught plus R. It is a form of it. You can get a common denominator the way that math people brainwash you. What the heck? So that's equal to HR naught minus HR plus H naught R little r over H naught. Quick check. Distributed the little h and then got the common denominator. Feeling good there. I did this 3 or 4 times and came up with 3 different answers. So I'm not opposed to making some careless error somewhere in here. All right, let's substitute in. So I had my volume then is 1/3 pi times h times that squared. H, let's see, h is my variable here.